In this video, I'd like to talk about exponential model word problems. So with these word problems, we're essentially going to be given some type of equation relating a real-world scenario where we have exponential growth or decay. And with these problems, we will come up with a strategy as we go through them. So a scientist measures the initial amount of carbon-14 in a substance to be 25 grams. The relationship A, the amount of carbon-14 remaining in that substance in grams, and T, the elapsed time in years since the initial measurement, is modeled by the following equation. So we have this equation here. And in how many years will the substance contain exactly 20 grams of carbon-14? So we need to express our answer exactly as a natural logarithm. And when dealing with word problems, when you're given an equation with different variables in it, it's a good idea to start by just defining what the variables represent. So we need to figure out, or we need to write in our own words, what is A and what is T. And the word problem will tell us exactly what these are. So A, that's the amount of carbon-14 remaining in the substance. So we can say that's the amount of carbon-14, and that's going to be measured in grams. So it's also a good idea to write down what the units are. And then T, that's the elapsed time in years. So T is representing time, and the unit for that is years. So now that we have a general idea of what this equation is representing, we can go and try to answer the question. So in how many years will the substance contain exactly 20 grams of carbon-14? So notice we're given how many grams of carbon-14 there are. And A, the amount of carbon-14, notice that the unit for that is in grams. So we're told the A value. We're told that A is 20 grams. And we need to figure out how many years that it'll take to get to this 20 grams. So notice the unit on our answer here, that's in years. So that's a hint that we're trying to find the time. So we know the A value and we're trying to figure out what the T value is. So let's make a little bit of room and we can plug in this information into the equation and then try to solve it. So we have that 20 grams is equal to 25 multiplied by E raised to the minus 0.00012 times T. And remember that E, that's just the number 2.718, and it's going to go on forever. It's an irrational number, just like the number pi, but it is the base of the natural logarithm. So it shows up a lot when dealing with exponential growth. So this is just a number here. It's not a variable like T or A. So we need to solve this equation, and when solving these exponential equations, the strategy is to first solve it for the exponential term and then rewrite it as a logarithm. So to do that, let's divide each side by 25. So we're just dividing both sides of this equation by 25. And 20 over 25, we can just simplify that to 4/5, divide top and bottom by 5. So 4/5 is equal to E to the minus 0.00012 multiplied by T. So our exponent contains the variable. So to get the variable out of the exponent, we want to rewrite this as a logarithm. And in general, remember when you have log base A of B equals C, that you can rewrite this as an exponential equation, or vice versa. If you have the exponential equation, you can rewrite it as a logarithm. But to go between the two, the logarithm and the exponential equation have the same base. So they each have base A, and logarithms are equal to exponents. So C is the exponent in this equation, and the input of the logarithm is what the exponential equation is equal to. So A to the C is equal to B. So in our case, we're given the exponential equation and we need to rewrite it as a logarithm. So let's do that over here. And the base of the logarithm will be the same as the base for the exponential equation, and it has base e. So we could write it as log base e of whatever our input is, but remember that a logarithm with base e, we just rewrite as the natural logarithm of whatever that input is. So we're going to have log base e, or in other words, we'll have the natural log. And remember that the logarithm is equal to whatever the exponent is. So we'll come back to the input, but the logarithm is going to be equal to that minus 0.00012 times t. Let me just make a tiny bit of room there. And the input of the logarithm, remember, is what the exponential equation is equal to. So 4/5 will go on the inside of our logarithm. And now we have an equation where we can actually solve for t, since it's no longer in the exponent. And to do that, we just need to divide each side by the coefficient on t. So we're going to divide both sides by this minus 0.00012. We'll again do that on both sides. So that on the right-hand side, they're going to cancel out. We just get t. And on the left-hand side, this is now equal to the natural log of 4/5. Let me make just a bit more room. Divided by minus 0.00012. And since our question is asking for an exact answer, this is what we'd put in the box. We would put the natural log of 4/5 divided by minus 0.00012 years. But if we wanted to find an exact value for that, we could do that as well. If you plug this into your calculator, this is approximately equal to 1,860, and remember, t is expressed in years. So remember, this is an equation, so we do have a way to check this. So let me just make a bit more room over here. So the way to check this, we figured out what we think is the correct answer for the number of years to get exactly 20 grams of carbon. So if we put in a t value of 1860, remember this is the approximate answer, we should get back an amount of roughly 20 grams. It's not going to be exact because this is not exact, but we can get a rough idea. So we're just going to plug this into our equation and figure out what A is. So then A would be 25 multiplied by E to the minus 0.00012 multiplied by 1860. And if we plug this into our calculator, we get roughly 19.99887, so 888, we can round it there. And this is very close to 20. So we can feel confident that this is the correct t value here.